Hi everyone, I'm Yinzhan. Today I'm going to talk to you about monochromatic triangles, triangle listing, and APSP. This is joint work with Virginia Veselowska-Williams. So in the all-edges monochromatic triangle problem, we are given an n-node graph G, where each edge E has a color. Our task is to determine for every edge E whether it appears in a triangle whose all three edges share the same colors. And we call such triangles monochromatic triangles. So for instance, in this figure, the only monochromatic triangle is the triangle 1, 2, 3. So we need to answer 1 for all three edges this triangle contains. And as we can see, there's no other monochromatic triangle in this graph. So we need to answer no for all other edges. The best algorithm for all edges monochromatic triangle runs in O tilde n to the 3 plus omega over 2 time, where omega is the square matrix multiplication exponent. This algorithm was given by Veselowska-Williams, and Euster. On the lower bound side, if we assume the three-sum conjecture, then no algorithm can achieve O n to the 2.5 minus epsilon time for epsilon greater than 0. And this was shown by Lincoln, Pollack, and Veselowska-Williams. Let me first introduce our first set of results, which strengthens the lower bound for monochromatic triangle via a strengthened lower bound to triangle listing problems. The previous lower bound to all-edges monochromatic triangle goes through this all-edges sparse triangle problem. So in this problem, we are given an m-edge graph G, and we need to determine for every edge E whether E is in a triangle or not. So note that in this problem, the edges do not have any colors. So the previous reduction first reduces three-sum to multiple instances of all-edges sparse triangle, and then reduce these instances to a single instance of all-edges monochromatic triangle. And both of these two directions are tight when omega is 2. The set disjointedness and the set intersection problems are two problems that are relevant to the all-edges sparse triangle problem, and both of them have three-sum hardness results. So roughly, the set disjointedness problem, in the set disjointedness problem, we are given a tripartite graph G on vertex set A union B union C, and we need to decide whether each edge between A and B is in a triangle or not. For the set intersection problem, given the same kind of graphs, we, instead of deciding whether each edge is in a triangle, we need to actually list a certain number of triangles in the graph, where this certain number is given also as an input of the problem. Previously, set disjointedness and set intersection were shown to be three-sum hard by Kopelowitz, Petty, and Porat. And many people have used these two problems as intermediate problems to show three-sum hardness for a lot of other problems, including dynamic maximum matching, dynamic ST reachability. Note that I'm not listing the running time of set disjointedness and set intersection here in the figure, because these two problems have some hyperparameters, like the number of vertices in each part of the graph and the density of edges. So based on these parameters, these two problems have different running times. In our mean result, we improve the previous lower bound to exact triangle hardness. So here, we replace the three-sum by exact triangle. So in the exact triangle problem, we are given a weighted graph, and we need to determine whether there's a triangle whose edge weights sum up to 0, sum up to t for some given integer t. The good thing about this new result is that it was known that both three-sum and APSP reduce to exact triangle. So now, all these problems, including all edges monochromatic triangle and dynamic maximum matching and a lot of other problems, not only have three-sum hardness, but also automatically get APSP hardness by one new result. Okay, so now let me switch topic and describe our second set of results. The notion of intermediate problems was first given by Lincoln, Pollack, and Wasilewska-Williams when they were studying the relationship among a set of problems whose running times are all tilde into 2.5 when omega is 2. And they call such problems intermediate problems. So for instance, the all-address monochromatic triangle problem is an intermediate problem. And the maximum problem and the maximum product problem is that given two n-bound matrices A and B, we need to compute a matrix C such that Cij equals the maximum over OK of mean AIK BKJ. The current best algorithm for maximum product also runs into the 3 plus omega over 2 time by Duan and Petty. Another intermediate problem is the unweighted directed APSP problem, whose current best algorithm is Zwick's algorithm. We essentially show a reduction from many other intermediate problems to the all-address monochromatic triangle problem. And the key step in our reduction is to define a new problem called all-address monochromatic equality triangle. So in this problem, roughly, we still also need to determine whether each edge in a graph is in a valid triangle or not. But here, a valid triangle needs to have 3 edges share the same color, so it's monochromatic. But at the same time, 2 of its edges need to share the same value, where value is a new attribute associated with each edge in the graph. So as you can see, this problem is harder than all-address monochromatic triangle. Let me first explain this arrow. So we show that if there exists a Tn time algorithm for all-address monochromatic equality triangle, then there also exist O tilde Tn time algorithms for all of the following intermediate problems, including the maximum product problem and the unweighted directed APSP problem we mentioned. So the other arrow, which is a dashed arrow in the figure, is not as clear as this reduction. So because this theorem depends on whether omega is 2 or not. We show that if all-address monochromatic triangle has an O tilde n to the 3 plus omega over 2 minus epsilon time algorithm for some 0 less than or equal to epsilon less than or equal to omega over 2 minus 1, then all-address monochromatic equality triangle has an O tilde n to the 3 plus omega over 2 minus delta time algorithm for some non-negative delta. And importantly, if epsilon is positive, then delta also needs to be positive. So let's first look at the case when epsilon is 0. Then apparently the precondition of the theorem is true. So that implies O tilde n to the 3 plus omega over 2 time algorithm for all-address monochromatic equality triangle. It means that all-address monochromatic equality triangle is indeed another intermediate problem. Now the trickier case is when epsilon is positive. So when epsilon is positive, this theorem shows that if we can improve a little bit over the current best algorithm for all-address monochromatic triangle, then we can also improve this all-address monochromatic equality triangle. And thus, by our previous theorem, improves other problems like maximum product. However, we have this upper bound epsilon here. So if omega is 2, this condition says that epsilon needs to be between 0 and 0. So epsilon cannot be positive in this case. Therefore, our theorem is limited in the case that when omega is 2, this does not imply any lower bound result. Okay, so in the remainder of this talk, I will focusing on proving the lower bound for triangle listing and showing how this lower bound can imply a lower bound for monochromatic triangle. Okay, let me start with some notions. An alpha beta gamma rho graph is a tripartite graph G whose vertex set is A union B union C, and the sizes of the 3 parts of the graph are n to the alpha, n to the beta, and n to the gamma, respectively. Also, we need some degree constraint on the graph. Let x and y be 2 arbitrary parts of the graph. Then, for any v in the part x, the number of edges between v and the set y needs to be bounded by n to the negative rho times the size of y. So essentially, roughly the edge density in the graph is n to the negative rho. Okay, let's see an example. So when alpha equals beta equals gamma equals 1, alpha, beta, gamma rho graphs are just tripartite graphs of n vertices, of all n vertices, whose maximum degree is O n to the 1-0. Okay. And we can define triangle listing problems on such alpha, beta, rho, gamma graphs. So given an alpha, beta, rho, gamma graph G, the alpha, beta, gamma, rho, T all edges triangle listing problem asks us to list up to T triangles for every edge between part A and part B. So here, up to T triangles means that if some edge is in at most T triangles, then we need to output all the triangles this edge is in. Otherwise, we can just output an arbitrary set of T triangles this edge is in. Okay. Now, our main theorem says that if we fix constants alpha, beta, gamma between 0 and 1, and 0 less than rho less than the minimum of alpha, beta, and gamma, we show that there exists a truly subcubic time reduction from exact triangle of n vertices to O tilde n to the 3 minus alpha minus beta minus gamma plus 2 rho instances of alpha, beta, gamma rho 900 n to the gamma minus 2 rho plus 1 OHS triangle listing problem. The expressions in the theorem might seem long, but in the remainder of the talk, I will just focus on this special case to simplify the methods. So when alpha equals beta equals gamma equals 1 and rho is at least 0.5, this theorem states that there exists truly subcubic time reduction from an exact triangle instance with n vertices to O tilde into 2 rho instances of 1, 1, 1 rho O1 OHS triangle listing. And recall that 1, 1, 1 rho O1 triangle listing, OHS triangle listing is just the problem of listing O1 triangles for all edges in a tripartite graph whose maximum degree is n to the 1-0. And we will focus on this case in the proof. So our proof actually reduces from the 0 triangle problem on tripartite graphs. In this 0 triangle problem, we are given a weighted graph, and we need to answer whether there's some triangle whose edge weights sum up to 0. And this problem is known to be equivalent to exact triangle. So that's why we can use it interchangeably with exact triangle. And we will use WUV to denote the weight between vertex V and U and V. Also, we can assume the edge weights are in FP for some sufficiently large prime P, because we can just take P to be 3 times larger than the maximum absolute value of all edge weights, and that will be enough for us. Okay. The first step is to consider FP as numbers from 0 to P-1, and we can split these numbers to n to the rho ranges, L1, L2, up to Ln to the rho. And also, we need to make all the ranges roughly have the same size. So they will have size P over n to the rho. Then we enumerate indices ijk, and at each time, we consider triangles ABC such that the weight between A and B is in the range Li, and the WBC is in Lj, and WCA is in Lk. We can soon realize that it is enough to enumerate ijk when we can pick up some number from Li, some number from Lj, and some number from Lk that sum up to 0. Otherwise, we don't need to consider the triples ijk. Then it's easy to show the number of such triples is only O into the 2 row. The difficulty here is that edge weights are not evenly distributed. So for some ijk, we might create some dense graph, but for some other ijk, we might create some sparse graph, but that's not good for our purpose. So what we do is to randomize the weights. We pick a uniformly random variable x from the field fp, and we pick, for each vertex u, we pick yu from the field uniformly at random. And then based on x and yu, we create the new weights. So in this figure, we artificially direct the edges. And for each edge pointing from u to v, we get its new weight by first multiply the old weight by x, and then subtract yu. Yu is the vertex we are pointing from, and then add yv, where v is a vertex we are pointing to. Okay, so if we look at the for any triangle ABC, if we look at the sum of weights, if we look at the sum of the 3 edges, it's easy to see that the sum of the new weights is exactly x times the sum of the old weights. Therefore, as long as x is non-zero, a 0 triangle remains a 0 triangle, and a non-zero triangle remains a non-zero triangle. So the set of 0 triangles keeps the same. And x is 0 with probability only 1 over p. If p is sufficiently large, this probability is negligible, so we can simply ignore it here. Okay, so for some ijk, we create a graph gijk, which is just g, but we only keep edges whose new weights are in the corresponding intervals. For instance, for any edge between part A and part B, we keep it only if it's in the range Li, and similar for the other 2 sets of edges. So even though we randomized the weights, some vertex in gijk might still have some large degree. So we still have to remove these vertices. And we do that by creating a graph G prime ijk, which is just gijk, but we remove all vertices whose degrees are larger than 200 times 10 to the 1 minus 0 plus 200. And recall that we are aiming to get a graph whose maximum degree is O(n) to the 1 minus 0. So this is good for our purpose. We claim that if gijk contains a 0 triangle, then G prime ijk also contains it with a probability at least 0.79. The proof goes like the following. So let's say ABC is a 0 triangle in gijk. Then for any B prime not equal to B, we look at the expression for its new weights. And notice that there's a minus YB prime term in here. Note that YB prime is independent from ABC and IJK. So it means that W prime, AB prime itself is a uniformly random variable, independent to the fact that ABC is in GIJK. Therefore, the edge AB prime is in GIJK with probability only into the negative row. Summing over every B, we get that the expected number of edges between A and capital B is at most n to the 1 minus 0 plus 1, where this plus 1 comes from the edge AB itself. And we can similarly bound the number of edges between A and capital C and get that the expected degree of A is bounded by 2 times n to the 1 minus 0 plus 2. So by Markov, we get that the degree of A is too large, only with probability at most 0.01. And by union bound, and we can do a similar analysis for vertex B and C, and then by union bound, we will keep all 3 vertices ABC with probability at least 0.79. Okay, so this is good because now G prime IJK is a 1-1 row graph, and we can run our 1-1 row O1 OIGS triangle listing algorithm on it. But note that our triangle listing algorithm do not know about the weights. So it's possible that our triangle listing algorithm lists many non-zero edges for edge AB, but it ends up not picking a zero triangle for the edge AB. So that's a bad case. So it remains to show that this bad case happens with only a very small probability. So now let's see C prime in capital C be a vertex such that ABC prime is not a zero triangle, but ABC is actually a zero triangle. So now, in order for ABC prime to be in GIJK, we need that the new weight of the edge AC prime and the new is fairly close to the new weight of the edge AC. So that means W prime AC minus W prime AC prime must be in this range, because LK has size roughly p times n to the negative rho. And we have a similar condition for the difference of edge weight BC and edge weight of BC prime. By some simple math, we can show that these two values are independent uniformly random variables. So starts 2 with probability roughly at most 4 times n to the negative 2 rho. Okay, so therefore, the expected number of such bad C prime is at most 4 times n to the 1 minus 2 rho, which is at most 4 as rho is at least 0.5 in our special case. So by Markov, the number of C prime is at most 400 with probability 0.01. So it suffices to list 401 triangles, where this extra one is for the actual zero triangle ABC. Now we showed hardness for listing all one triangles on every edge, but in order to get a reduction, in order to get a hardness result for all edges monochromatic triangle, we need some hardness for a problem on detecting whether each edge is in a triangle or not. But luckily, by standard techniques, these two problems are equivalent up to polylogarithmic factors. So this essentially finishes the reduction from exact triangle to all edges monochromatic triangle. Okay, so that's it. Let me give a brief summary of our results. We first show that many threesome hard problems are now also APSP hard. This is a reduction from exact triangle to set disjointedness and set intersection. Our second set of result is that all edges monochromatic triangle is in some sense a hard problem among intermediate problems by this reduction. Okay, thank you for listening.